Welcome to this primer on the well-ordering principle. In this lecture, we'll introduce what is the well-ordering principle and look at an application. So let us start. All we need to know is what are natural numbers, and I can't say much about what are natural numbers. So this is something that I take for granted, and one can build mathematics on this foundation. So I'm assuming that one knows how to add natural numbers, how to compare natural numbers. So for example, 3 is greater than 2 and all those things. So that is a given. And now let us state what is the well-ordering principle. So the well-ordering principle says that every non-empty subset of the natural numbers has a smallest element. Right? That is what the well-ordering principle says. So let me expand on that. What does that mean? So it says the following. Suppose, if S is a subset of the natural numbers, which is non-empty, such that S is non-empty, then there is an element in S such that it is not more than, or it is the smallest element in S, right? So this inequality holds for all elements of S. So that is the well-ordering principle. Whenever you have a non-empty subset of the natural numbers, it has a smallest element. And of course, the smallest element will be unique. There are not going to be two different smallest elements. Okay, so this is something that we will use. One can try proving it, but one will be going around in circles. So I take this as the starting point and deduce other things from it. Okay. There is a functional version of the well-ordering principle, which says the following. So what does it say? Let me write down. So it says that says the following. So let S, so f be a function from a non-empty set A to the natural numbers. Then there exists an element in the set A such that the value of the map at the point A is the smallest possible, is the smallest amongst all values that the function takes. Right? So I hope this statement is clear, meaning there is a point here which takes the smallest value. And this is just a consequence of the previous one. So let me prove it. So to see why, let S be equal to the image of the function S, which by definition is this thing. Right? That is the definition of the image, and this is the non-empty subset of the natural numbers. And therefore, by the well-ordering principle, we can find, it has the smallest element. So let S naught be the smallest element of S. Okay. So now so since S naught is in the image, we can find some A, or let's call it A naught, in the set A such that F A naught is S naught. Right? S naught is after all in the image of F, and hence there is some element in the domain of F whose F value is S naught. Okay, so we have this, and now if A prime in A is arbitrary, then F A prime is of course in the image set, and hence S naught is at most F A prime, because S naught was the smallest element in the image set, but S naught is nothing but F A naught. And that's it. That proves this functional version. We have found a point A naught in the domain, which satisfies this inequality for all A prime, because A prime here was arbitrary. This is for all A prime in the set A. And now one final remark. This A naught may not be unique. There may be multiple such A naughts. You just take the pre-image of this singleton. All the things in the pre-image will satisfy this inequality. So it's not like this A naught is going to be unique. Only S naught is unique. S naught is an element, is the smallest element of S. So there is only one such element, but there may be multiple such things in A which map to the same point. So it is a deceptively simple fact or statement of mathematics. It should be intuitively obvious why this is true, but it can be used in amazing ways. So let me try to give one example where one can use this, and I will do everything in gory detail, but one should try to understand the core of the argument. So here is the example. Suppose n is some positive integer, meaning some natural number, and suppose S is a subset of this set. Maybe S is a bad idea, but anyway, so let's say S is a subset of this set whose size is n plus 1. Or maybe I could even say at least n plus 1. Okay? Or maybe let's leave it at that. It's the same thing. So suppose its size is exactly n plus 1. Then we want to show that there exist distinct x and y in S such that x and y are relatively prime. So what does this mean? Relatively prime means the greatest common divisor of x and y is 1, which means that they do not share any prime factors. So if p is a prime and it divides x, then it cannot divide y. And if p is a prime that divides y, then it cannot divide x. That's what it means. So I hope relative primality, the notion of relative primality is clear. And now let's prove this. So since this is the first time we are going to show an application of the well-ordering principle, we'll do everything in great detail. But generally, when a proof is written using the well-ordering principle, it is not going to, be so expressive. And that's a good thing. But for now, we have to bear with all the details. Okay, so we want to prove the statement. So fix an n. And we say that n is good if whenever S is a subset of 1 up to 2n with, so maybe I will put greater than equal to here. It's just easier for me. It's the same. The problem doesn't change, but I'll just put greater than equal to there. Okay, so whenever S is a subset of the first 2n integers with its size at least n plus 1, one can find distinct x and y such that x and y are relatively prime. Okay, so such a, any natural number is said to be good if it confirms to the proposition. All right. So basically the problem asks us to prove that every natural number is good. So this is just a restatement of the problem. Okay. So let us collect all the bad natural numbers. So we have collected all the bad natural numbers which do not conform to the proposition. So the goal of the problem, just a restatement of the problem, is want to show that B is the empty set. Right? That is the goal. And how do we proceed? So we will proceed by contradiction. So assume on the contrary that B is not empty. Right? And we want to bring a contradiction. So if B is not empty, then by the well-ordering principle, there is the smallest element in B. So there is the smallest bad natural number. So by the well-ordering principle, let be the smallest element in, right? So by the well-ordering principle, since this is a non-empty set, it has a smallest element which we are calling n naught. Okay. And now note that n naught is greater than 1. Why? Because 1 is definitely a good natural number. you can easily verify the proposition for n equals 1, and hence 1 is definitely good, and hence it is not in the bad set. So it cannot be equal to n naught, right? So n naught is definitely greater than 1. Okay, and now since n naught is bad, there is a counter example to the proposition for this particular value of n. So there is some s naught contained in the first 2 n naught integers whose size is at least n naught plus 1. And one cannot find two distinct elements in S naught which are relatively prime. And which are relatively prime. Okay. And now here is the final, the main point of the argument. So we make this list 1, 2, 3 up to twice of n naught minus 1. And the last two integers, we want to treat them as somewhat special. Okay, we have this list. And let us say T naught is S naught intersection this part. Okay, so that's our T naught, and there are two cases. So case 1. Case 1 is that T naught is at least n naught in size. And note that n naught is twice of n naught minus 1 plus 1. Sorry, what have I written? It's n naught minus 1 plus 1. So now if T naught, so let's just finish this case. What we will do is first use the fact that this is good. Why is this good? This is good simply because n naught was the smallest bad thing, and hence anything smaller than n naught is going to be good as long as it is a natural number. And it is a natural number simply because n naught is greater than 1. So this is greater than equal to 1. This is a natural number, hence this is good. So since n naught minus 1 is good, we can find two distinct integers in T naught such that x and y are relatively prime. So we are using the goodness of this guy and the fact that the cardinality of the set T naught. So first of all, T naught is a subset of twice of this good, the first twice of this natural number, and its size is at least 1 plus this good natural number. So therefore it is applicable, the goodness of n naught is applicable here. So this is just a consequence of the goodness of, sorry, I said goodness of n naught. The goodness of n naught minus 1 is applicable here. So this is just a consequence of goodness of n naught minus 1. And case 2 is that this is strictly less than n naught, or one may write it like this. So in this case, what happens? In this case, see, the point, the size of the set S naught is at least that much, and the size of T naught, meaning within this part, it is having at most these many things. So to have this constraint maintained, both of these have to be included in S naught. So then both of these are in S naught, but they are clearly relatively prime and distinct, because any two consecutive integers are relatively prime. So that's that. And in any case, in case 1, we can find two distinct integers in T naught and hence in S naught, because T naught after all is just a subset of S naught. So in case 1, we can find two distinct integers in S naught which are relatively prime. And in case 2, we can explicitly write down the two relatively prime integers in S naught. So therefore, in any case, S naught has two distinct relatively prime integers. And that finishes this proof. So this is like a long way to write a very short proof. The shortest way, or the standard way to write it, would be assume on the contrary that this is false, and then you pick the smallest integer which invalidates the proposition. So the proof will then start here. It'll just say that let n naught be the smallest element for which the proposition is false, and then you note that it has to be at least 2, meaning strictly greater than 1, and then you just repeat this reasoning. So the length of the actual proof would be this, and if you are at an advanced level, it will be even, the writing would be even less. Anyway, so just try to get down to, just understand this template. You want to prove a proposition for all n, you collect all the bad n's, you pick the smallest bad n, and then you somehow, using some inspiration, this is the inspirational step, you try to find a contradiction. You go one step lower. If you go one step lower, you know that you are at a good integer, and then you somehow use the properties of the problem to find a contradiction. Okay, so I hope this was useful. As usual, like, comment, share, subscribe, and I'll see you next time.